who's going to speak on formal verification for designers. Sergio is technical marketing manager at OneSpin and has 20 years experience in electronic chip design and deployment of advanced hardware development solutions across Europe, North America and Asia. His expertise covers IC design, functional verification, safety standards including ISO 26262 and DO 254, and detection of hardware trojans and security vulnerabilities. He is passionate about enabling the next generation of high-integrity chips to underpin the Internet of Things, 5G, artificial intelligence, and autonomous vehicles. And he's in Spain today. Over to you, Sergio.
Hi, yeah, thanks. So I think this talk is going to fit well with especially with the first two talks, and I'm going to go through a range of things that designers can do using formal to boost the quality of their RTL code before they commit their code. So OneSpin provides IC integrity verification solutions, which is not only the traditional functional correctness functional verification, but also safety and trust and security. And this talk will focus on functional correctness, finding functional bugs, but some of the things could also apply to the other different pillars. But yeah, our focus is functional verification. So if we look at the cost of fixing hardware bugs, there isn't really a lot of good high quality data available. There are some studies, mostly on software, which are referenced into the slide if you want to take a look. But I mean, there is a general consensus that I mean, the cost of fixing a bug increases exponentially as you know, the project stage evolves. And I mean, there is an obvious interest in catching bugs as early as possible. And we are going to look a little bit, you know, at the RTL development stage in more detail. So if we look at the RTL development process, this is one scenario where, you know, you can have a designer, let's call it Sarah, just, you know, and the verification engineer, Mike. So any reference to the organizer is just by chance. You know, maybe Sarah is lucky enough to have actually a nice high quality test bench with a verification plan built for her module. And when she hands over the code, some good quality regression is run by Mike, or maybe even a couple of verification guys. That could not be so unusual. And you know, the report fails. And of course, there's going to be some interaction there because, you know, there's a fail, maybe it says, oh, this is actually a feature. Then it turns out the test is not good, the test gets fixed. And, you know, finally, it turns out there was a bug into the RTL, it gets fixed. But we can see that this, you know, has consumed some dollars, tools, but mostly engineering time. In a different scenario, more complex scenario, we could have, you know, many designers and maybe a team of a verification team that was building, you know, a big test bench with lots of tests. This is actually a very usual scenario. You know, when a designer checks in some code, it will go, you know, into this bigger project. And then when the verification team runs the big regression and some fails turn up, you know, there's going to be potentially a lot of communication going on to sort out fails. Even if you use advanced triaging techniques, there's still, you know, going to be a lot of dollars spent, I would say, because you might have multiple verification engineers, multiple designers involved, maybe different time zones until you track down the issue to Sarah again that made the check-in with the bug. And by the way, of course, there can be quite some time passing by, you know, between, you know, the check-in and the actual bugs being found. So these are, let's say, two fairly typical scenarios. So of course, in these scenarios, I think it's normal that regression find bugs. That's a job, but probably designers and in general any engineers, I would say, it could be worth asking, you know, could I have found this bug before I committed the code? Because obviously that would have provided, in many cases, a very significant saving of time by not involving all these people. And you know, formal, I think it can provide a lot of tools to catch a lot of bugs earlier, and you know, enable designers to catch bugs before they commit. And yeah, I think that's the main message, you know, to designers: formal is your best friend. So if we look at the use of formal and assertion in the design community, just want to give a kind of a history bit with the Open Verification Library, which kind of started in 2001, was standardized in 2005. The last release was in 2014, and I think this enjoyed some success. You know, with the designer using this you know, this library of assertions that could be used, you know, with the potential with formal in simulation, so interoperable, you know, nice prepackaged, so that the entry barrier was low. And yeah, I think in its days it enjoyed quite success, and I mean, obviously there are still people using it for sure. But there are a lot of other things you can do with formal, and one of the things that I would always start with is design inspection, where you know, you compile the RTL, push a button, and you get a range of checks. Some, let's say, linting checks, which we see that sometimes designers even prefer, you know, to complex linting tool. You know, personally, for example, I would not recommend to have complex linting flows where you have a lot of waivers to manage, because that's maybe not a good idea. But on top of all this linting with formal, what you get is you get a lot of assertion automatically generated for you that you can check. And I think the important point here is that assertion can find a lot of simple bugs, but also corner case bugs, because as soon as you have an assertion, even if it's automatically generated, it can fail in deep corner cases. So obviously, if you find a bug that could have been detected during a regression, that could have been detected with this kind of flow, it's a real shame, because it's a lost opportunity to make a huge saving. Another thing that the designer can do with formal is design exploration. You know, unlike, for example, with UVM test bench, where you need the code, you know, writing some code, maybe use tool to automatically generate some code for you. Here, you don't really need any code at all. Again, just compile your design and say, for example, I want to cover this, I want to hit this line of code, I want to hit this FSM state, and the tool will automatically generate basically a test for you, all the stimuli to hit that coverage target. So it's really easy to use, and can be used also, for example, for legacy design, if you want to understand better how a certain design works. That, you know, again, I have personal experience in using this, and very, very easy, and does not require formal expertise. Another interesting application of formal is sequential equivalency checking. In this case, you know, if you, for example, are making some incremental changes to a design to introduce scope gating, to do some FSM re-encoding, or some cleanup, you can have, you know, your original RTL and your modified RTL, and if you expect that the input-output behavior of the module does not change, again, this is immediately something that you can do with formal. You compile the two design, push a button, and you can see if the two versions of the design are sequentially equivalent. And for example, I used this to clean up some code in a module that was not mine, RTL code. So I, you know, obviously, because I wasn't totally sure about the changes I was making, removing signals that I thought were useless and things like that. So I continuously run formal sequential equivalent checking, you know, to make sure that I was not altering the functionality of the model, but I was only cleaning up what was useless. So that's another very good application of formal. I would say the next step perhaps could be for designers to use some formal apps. For example, bus protocol verification IP, or if you have a floating point unit, it's also very easy to use, you know, formal for floating point verification. And in this case, again, you don't need to be an expert of formal. You don't even need to know the module very well. I personally use, for example, these many modules. One example is a module had an AXI3 interface. I'm not an expert of the protocol. I didn't know the module, but as soon as I see the interface, you know, it takes me one command to instantiate the verification IP and push a button and run some properties and find some potentially some corner case bugs that again would be a shame to be found at the regression step when they could have been found so easily early on. Again, moving one step forward, that is probably writing your own properties. That's great, of course, for designers to do that. In this case, you will need to learn the language, writing some SPAs or PSL. And probably in this case, I would recommend it, for example, for if you have custom interfaces where your neighboring designer, you have some kind of unwritten agreement how the interface is working. It might be a good idea to capture this in a more executable way, let's say using a session, check them in simulation and formal, because many bugs in my experience come from this kind of unwritten protocol specification. Another thing could be for a designer to define some coverage points, some maybe white box scenario where, I don't know, if IFOP gets full when a state machine is into a certain state, it's very easy to write this kind of coverage point, and then you could challenge the verification team to write the test that hits this coverage point. Maybe a word of warning is like to not write a lot of small assertion here and there, because of course you might want them to maintain this, and if you write a lot of white box assertion and you make design changes, a lot of assertion will fail. You have to maintain them. So I would maybe suggest that if you are very keen into writing assertions, even white box assertion, that's great, but perhaps it's worth to make a plan, a bit of strategy, how you want to handle that. Maybe the holy grail of applying formal could be what I call agile RTL development. In this case, I would say the aim would be, the possible highest aim, where you say, okay, I really don't want the verification team to find any bug in my module during regression. So of course, you cannot run something that is overnight or even a weekend regression before you do a check-in. And I have an experience, using a formal in a sort of agile way, pairing a designer with the formal verification expert and developing kind of properties in lockstep. And as the design evolved, so while the design was being coded, and the crucial thing here in this type of application is that with formal you can run all your checks. Maybe you don't have the time to run all your checks for a long time and get full proofs, but you can run them all and maybe assign half an hour for a quick regression, so to speak. And formal is very good to detect issues quickly. So even if you don't get the full proof, but you run all check for half an hour, total runtime, you get a very high confidence that the big long regression will not find issues. And for example, with one spin, the tool automatically set up, you can easily set up strategies to distribute the allocated time over all the checks, parallelize them, and do a lot of bug hunting. And this was quite successful in this actual experience. There is also a link down there to an article if you want to take a look, and this was really reaching the ultimate goal of running this very high quality but still quick check before the commit. And also the other thing that this kind of flow enables is a lot of quick iteration, because for example, we had occasion with the designer where we make a change, run this quick regression, find the problem, reiterate again, make maybe a big change, but that could be validated with a lot of confidence with this process, and then after a few iterations, got the pass from this quick check and then commit. So in conclusion, I would say that formal is really designer best friend. You can boost the quality of your RTL code before you commit with the range of solution from fully automated design exploration to more advanced ways of using formal. And really, there is a range of solutions from absolute beginner to advanced. In terms of flows, for example, OneSpin support ASIC and FPGA flows, Verilog system Verilog VHDL design, and something maybe you don't know, we also support system C and C++. So many of the things we said can also be applied to system C design that targeting, for example, HLS. We provide also designer-specific training and support. I mean, obviously, a designer doesn't need to turn formal to run auto checks, for example. It can be, literally a couple of hours to do the basic, compile the design and get it up and running. And this kind of flow has been also successfully integrated, like in corporate continuous integration flows. So it can be kind of be part of the corporate flow. And of course, the huge advantage is that minimize the RTL bugs found during the regression, providing a lot of savings. So that's all for me. Do you have any questions?